Okay, today we're looking at exercise 2.2 of our textbook, starting with an introduction to vectors in the plane. So our learning goal for this video is I'll understand the difference between vector and scalar quantities, and I'll be able to notate and compute simple vector diagrams. So we can see in that first goal, we've got the cognitive verb understand in green there. We want to make sure that we know exactly what's going on there. And then in the second one, we've got, well, they're not really cognitive verbs, but they're more actions that we're going to be doing, notating and computing simple vector diagrams. So hopefully by the end of this video, we understand those blue terms and are able to achieve those green terms. So when looking at vectors, we compare them to stuff that we're already familiar with, scalar quantities. So for instance, time, mass, area, these are all known scalar quantities that we've been working with since like grade 3. So scalar quantities have what we call magnitude only. Vector quantities, on the other hand, so for instance, velocity has direction as well as magnitude. And if you've seen the movie Despicable Me, the main villain in that has a little quip at the start of the movie because his name is Vector, that he commits crime with both direction and magnitude. So a little Easter egg that you will now understand with your big maths brain. Vector notation is shown graphically as a line with a tail at the start and head at the end. The length of the line indicates the magnitude. And the orientation of the line indicates its direction. When writing this vector, we can use A, B with an arrow over it, and this is read as the vector from A to B. Some textbooks use a single letter in bold, such as W, but this is difficult to write using pen and paper, so instead we draw a squiggly line underneath the W, and that symbol is called a tilde. Okay, so great. We know how to construct a vector, but what if we want to know if two vectors are equal? Well, to be equal, you need to have both magnitude and direction being exactly the same. So from the figure here, we've got 4 different vectors. We can see that these 3 vectors, U, V, and Z, all share the same direction, but only one pair of them is equal. So when looking at this, we can see that the vector V has the same magnitude, whereas Z is a little bit longer. So the only vector that is equal here is V. U has the same magnitude as V, but a different direction. And we can see that U has the same magnitude as W, but a different direction. Okay, so we now know what 2 equal vectors look like. What if we want to add them? So consider a vector U over here that measures the travel from A to B, and vector V that measures the travel from B to C. The net result is as if a person traveled directly from A to C. So skipping B entirely, and that gives us the vector W. So we can say that W is equal to U plus V. So it's almost as if, and I'll do this in orange, if I were to travel up here and then travel down here, that's the same as just traveling along that blue line there. I've started at the same point, I've ended at the same point, I've just done a lot fewer steps. So to add 2 vectors, we take the tail of one vector, join it to the head of the other. So we can see at that point B, we have head to tail addition. The negative of a vector. So if U is the vector from A to B, the negative U is the vector from B to A. So subtraction is really just negative addition. So instead of adding the original vector, we add the negative of the second vector. And that's sort of our workaround for getting subtraction when all we can really do is add. We just add the negative vector. So let's put this into play. Example 1. Use the vectors shown at the right. Draw the results of U plus V, negative U, U minus V, and V minus U. So let's start with part A. So if we have U plus V, as it stands, we have a small issue, which is that our heads are not matching up with our tails. So we have to do in our minds sort of a horizontal shift of this v component so that the tail matches up with the head of u. So that's still v. All we've done is sort of moved it on our page. So then the resultant is going to be an arrow going from our start to our end point. So this is u plus v. So all we have to do is draw an arrow with that same magnitude and direction. So it's going to look something like that. And we can sort of acknowledge our two vectors that constructed it. Okay, part B, we are looking at negative u. So it's the vector u, but now in the opposite direction. So instead of being an arrow to the right, it's an arrow to the left, and we try to get that magnitude to be the same as well. Okay, now looking at part C, we've got the vector u minus the vector v. So v is now coming down instead of going up. So what we can do is take this v that we've already drawn over to the head of u and draw it in the opposite direction. So it's now coming down with the same magnitude. Let's actually make that line a little bit longer just so that we can see that magnitude in play. And now our resultant is going to be coming down. So this is u take v, and we're going to draw that in our part C area. So it's coming down, and we can draw in our other vectors. It's getting really hard to draw these arrows. Let's try that again. So that's that's positive u. And that is negative v. So this is u take v. All right, and last one, part C, we now have positive v plus negative vector u. So u is now going in its opposite direction that we already determined in part B. So we can consider the v that's already drawn in the question and flip the u so that its head is at the tail of v. So I'll draw that in sort of this gray color here. The head's now going to be there. So the resultant is going to come up from the base of negative u. Let's undo that. The base of negative u. I'm just going to go to the top of positive v. So our resultant's coming up like that. Our vector u is coming to the left. And our vector v is going up this way. But there's one thing I forgot, that is negative u. So this vector here is going to be positive v minus the vector u. Okay, and that's example 1 done. Okay, example 2 asks us, let's just get rid of that symbol. Okay, example 2 asks us, the parallelogram A, B, C, D can be defined by the two vectors B and C. In terms of these vectors, find the vector from A to D. So if we're traveling from the point A up to the point D, we are traveling through the vector that is equal to the vector C. So even though that vector C is over on the right here, the displacement that we're doing, the path that we're taking is exactly the same as the path we'd take if we were going from B to C. So we can say A to D is equal to B to C, which is equal to vector C. So that's our answer for part A. Part B is asking us to go from C to D. So similar idea there, but we have to note the direction of B. So B is going to the right. If we're going from C to D, we're going to the left. So C to D is going to equal negative A to B, which is going to equal negative B. And our last one is from D to B. Now we're going diagonally, so we can see that going from D to B is the same as taking the path B and then going the negative direction of path C. So D to B is equal to D to C minus B to C. And we already know that C to D is negative B, so that's going to be positive B. And we know that B to C is positive C, so if we're minusing B to C, then that's going to be B minus C. So that is our vector from D to B. So now we take that idea with the parallelogram and we apply it to a cube. So the cube PQRSTUVW can be defined by the three vectors A, B, and C. In terms of A, B, and C, find the vector joining P to V. So going from P to V, we can see we follow the path A and we follow the path B. So P to V is equal to A plus B. What about P to W? Well, now we're going up the diagonal, so we have to go through the path A, through the path B, and then also through this path C. So that's going to be P to W is equal to A plus B plus C. Okay, part C, from U to Q. So we're starting at one side and we're going to the other. So we're going the same direction as A, but now we're going the negative direction of B. So U to Q is going to be A minus B. For part D, we've got S to W. So we're taking the path of A, we're taking the path of B. So S to W is actually the same as P to V, which we already know is A plus B. And the last one we have is the vector joining Q to T. Well, that's going to go up C minus A plus B. So we could write that as, what is it? Q to T is equal to C plus B take A. So that's how we write those vectors joining those vertices in this cube in terms of three vectors A, B, and C. Okay. So once we've got our vectors set up, we can take multiples of vectors. So for instance, we have these three vectors off to the side here, u, 3u, and negative 2u. So we see when we multiply by a positive scalar bigger than 1, we're increasing it. A positive scalar less than 1, we're decreasing it. And then if it's a negative scalar, we're also changing the direction. So if a vector u has a direction of north and a magnitude of 10, then the vector 3u is still going to have a direction of north and a magnitude of 3 times 10, which is 30. And this brings in a good point talking about the direction of north. So often directions are going to come in 3 different forms. You're either going to have an angle from the positive x-axis, or you're going to have a compass direction, or you're going to have a true bearing. All 3 of those are generally the most common directions that you're going to see for a vector. Okay, if the scalar is negative, the direction is reversed. Therefore, negative 2u has a direction of, well, what's the opposite to north? We can see up at our compass that that is going to be south. And that will have a magnitude of 20. We don't write negative 20 because magnitude is always positive. It's a length, right? A length of the vector, if you will. You can't have a negative length. Even though this is going in the opposite direction, it's still going to be 20 units long. Okay, so using the vectors shown at the right, draw the result of 2r plus 3s and 2s minus 4r. So for part A, if we line up 3 of these s's, so there's 1, there's 2, there's 3, and then 2 of these r's, so that's our s's. Excuse the drawing on the tablet. We can see that our resultant is going to be up like that. And then for part B, we have 2s minus 4r, so our direction is now changing. So if we have our 2 s's coming in like that. And then we have our 4 R's now going to the right instead of the left. So we got 1, 2, 3, 4. We can see that our resultant is coming through like that. So let's label these resultants. We've got 2S minus 4R and 2R plus 3S. So all we're really doing is repeated addition, right? We're adding the vector R 4 times, we're adding the vector S 2 times, or in this case subtracting. That brings up a good point. These should be negatives. But yeah, it's so scalar multiplication is just repeated addition, very similar to if you were to multiply as in scalars. 2 times 3 is just 3 plus 3, it's 6, right? So repeated addition is the foundation of multiplication based off set theory, which is something we're not even going to try to cover today. Okay, so last example is example 5. We've got a boat, travels 30 kilometers north and then 40 kilometers west. So we can see that we're now applying vectors to a physical scenario. So we have to make a vector drawing of the path of the boat. So they're traveling. I'm actually going to bring out the ruler for this just so that we get that proportionality. So 3 of these ticks, I think this ruler is in inches, but let's just use it for this sake. So 3 of these ticks is going to represent 30 kilometers. So 1, 2, 3. And then we want 4 ticks for our westward direction. Let's try and line this up. One, 2, 3, 4, just barely fitting it in. Okay, so the boat travels that 30 kilometers north and then 40 kilometers west. We want to draw the vector that represents the net displacement of the boat. Now, distance is a scalar, displacement is a vector. So we care about the direction that this boat traveled. Well, it started at this point and ended at this point. So it's going to have a displacement that looks like that. What is the magnitude of the net displacement? Well, we'll notice that with these two distances, north and west are at 90 degrees to each other. So this triangle that we've created is a Pythagorean triangle. And more important than that, it's actually a Pythagorean triad. We've got a 3, 4, 5 triangle here. So we'll still do the maths correctly. We take 30 squared plus 40 squared, and that's going to give us 50 squared. So we can see that this is like 10 times bigger than a 3, 4, 5 triangle. So we get a nice round 50 kilometers as our net displacement. And then if we were to calculate the bearing from true north of this net displacement vector, well, that means we're looking for the value of this angle here. Oh, it's true north, so actually we want it to go around like this. But to do that, we first need to know what this inside angle is. So how do we find theta when we've got a right angle triangle? Well, we just apply trigonometry. So part D, that angle, we are fortunate in that we have all 3 sides. We could choose any of them. I'm going to choose 30 and 40 kilometers. And this is something that I want you to start keeping in mind. When you're given the choice between different numbers in your question, you always pick the numbers that are given to you from the start. If I had messed up that 50 kilometer calculation, then I choose it for this part, we're going to have an error carried forward. But I have the choice to choose 2 numbers that are actually given to me in the question. So by choosing those, I know that even if my answer for part C is incorrect, my answer for part D is still going to be correct. So we're going to use the tangent function. Opposite is our 40, and our adjacent is 30. So theta is going to be the inverse tan of 4/3. And tan inverse of 4/3 is 53.13 degrees. That gives us the angle theta, but what we want is the true bearing. So we have to take that away from 360. So 360 subtract 53.13 is, of course, equal to 306.87 degrees true. So that gives us the bearing from true north of this net displacement vector for part D. That's all for exercise 2.2. Thank you for watching.